The final section that we have to look at in organic chemistry and in the year is looking at organic derivatives. Organic derivatives are any one of a number of classes of hydrocarbons, meaning that they have a carbon backbone with hydrogens attached off of them, which have additional and important functional groups attached to them. And these functional groups largely contribute to the properties of the molecule, although it's also important that they would have a certain number of carbons that might determine in part whether or not the substance becomes a liquid, a solid, or a gas. The functional groups will give a lot of characteristic properties to the molecule. The functional groups may include any of the following: a hydroxyl group, which is an OH group attached off of the carbon chain, a carbonyl group, a C in the chain double bonded to an O, a carboxylic acid, where you have a terminal or an end carbon, which is double bonded to an O, and as well bonded to an OH group, an ether, where you have an oxygen joining two individual chains, which may or may not be the same length, and an amide, which has a NH2 group at the end. Now, alcohols are the first group of hydrocarbon derivative, and they're identified because they have a hydroxyl OH group bound to a carbon somewhere in the chain. When we name alcohols, we add the ending OL as a suffix to the name, and the root would depend on whether it was an alkane, an alkene, an alkyne. So looking at an example of this, we have this particular molecule, and we're going to look just like before for the longest possible carbon chain. That longest possible carbon chain should be one that includes or has attached to it the OH group. So although you might be tempted to go side to side here, we can see that if you swing up and around and then down and over, we have a 5 carbon chain instead of a 4 carbon chain. That means that this is a pent group. Now, because it is a pent group which only has single bonds between the carbons, this would be a pentane. Now, I'm going to leave off that ending for just a second. Now let's deal with the part that we actually know about already, and that is looking at how to number the carbon chain. When we had alkenes, the double bond was the most important group, so we had to number it to give it the lowest possible number. When it was the alkynes, the triple bond was the most important group, so we had to number the chain so that it had the lowest possible number. Same thing for the alcohol. When we number, it should be giving the hydroxyl, the OH group, the lowest possible number. In this case, you wouldn't be tempted to number it the other way anyway because you get a lower set of numbers in the same direction. So I'm going to start on the right. 1, 2, 3, 4, 5. Now, because this is a hydroxyl, an alcohol, we change the ending of the pentane to an ol. But just like before, when we had double bonds, we have to say where in the chain that double bond, or this, in this case, the hydroxyl group is. The difference here is that because you can have alcohols which are on alkenes or alkynes, we don't put our number in front of the pentane or in front of the pentene, etc. You put it between the ane, ene, and the ol. So in this case, our ol group is attached to the second carbon. The last thing we have to do is look at the fact that there is another group attached off of the main chain. We have this 1 carbon group. 1 carbon represents meth, and because it's a substituent off of the main chain, this is a methyl. Now that methyl group is attached to the 3rd carbon. So this is 3-methyl pentane 2-ol. We already know that there's no spaces in names, but that numbers and letters can't touch. So they must be separated by dashes. So I'm going to insert 3 dashes to make this 3-methyl pentane 2-ol. The next ones we're going to look at are called ketones and aldehydes. And aldehydes and ketones both happen to be identified because they have a C double bonded to the O. The determining factor of whether this is an aldehyde or whether this is a ketone is where in the chain that C double bonded O is. When we look at an aldehyde, aldehydes have the C double bond O at the end of the chain. It's a terminal one. So it would look something like this at the end. Notice that carbon always has to have 4 bonds. 2 of those bonds are taken up to an oxygen. 1 would be to the remainder of the chain, so there is also another hydrogen attached. Aldehydes are named by giving the suffix al, al, just in the same way that we added the ol ending to alcohol. When we look at ketones, ketones have a C double bonded O, a carbonyl group as well, but this C double bonded O is in the middle of the chain. So it would have C bonded to 2 other things, and it would also have a double bond O off of the chain. Now what you would see is that in both of these cases, and in fact in any organic compound, that we would write the remainder of the chain with a letter R, to indicate that there is some number of carbons off of that chain. It may be 1, it may be more than 1, but it has to indicate that there is another carbon chain extending on both sides there for the ketone. When we name ketones, they end with the suffix ONE. Again, they're named in a very similar way to what we did with alcohols. So let's look at 2 different examples here. And these are very similar. They're both 3 carbons long, a 3 carbon chain here, and a 3 carbon chain here. The distinguishing point is that this has the aldehyde carbonyl group because it's a terminal one, whereas this has the ketone carbonyl group because it's within the middle of the chain. Looking at the aldehyde, this is a prop because it's 3 carbons long, and all those bonds are singles, so it's an as opposed to an or an ein. Similarly, looking at the ketone, this is again a prop, and again an because all the bonds between carbons are single, but now it's a ketone. So looking at how we place the name at the end of the chain here, we see that with the aldehyde, we add an Al. The difference here is that because there are no functional groups, there's only one way in order to number the chain. 1, 2, 3. If you happen to flip it to the other side, so you numbered from the left, that would have to be where the aldehyde group was as well. So it doesn't actually require a number in this particular case. Similarly, for the second example, because we only have one internal position in which we can place the ketone carbonyl group, this is simply propanone. I wouldn't consider it wrong if you wrote propan 2-one or propan 1-al for the aldehyde, but other people may at a university level. Looking at the next group of organic derivatives, we have carboxylic acids, and carboxylic acids are sometimes called organic acids because they contain a COOH group. What that would look like is you've got a carbon bonded to an oxygen, but it's not just bonded singly, it's double bonded to the oxygen, meaning that that bond between them is very, very strong. And then you have also another bond to an oxygen, which is then bound to a hydrogen. This carbon, because it needs 4 bonds, would then be bounded to the remainder of the chain. So when we look at this group, the reason that it acts as an acid is that it's bonded to 2 oxygens. We know that relative to hydrogen and carbon, oxygen happens to be very electronegative, meaning that it will pull electron density towards it. Because there's not just 1 but 2 oxygens bound to the carbon, this bond between the oxygen and the hydrogen is very weak, even though it's covalent. So carboxylic acids, like other acids, will donate this hydrogen, when a base comes along to remove it, and as a result you end up with the R group bonded to the O and the now negative oxygen, and you have the base bound to the hydrogen. The base generally will be negative, so that will balance out some of the positive characteristic of the positive hydrogen that it's stolen from the organic acid. The last two groups that we have to be able to recognize only are called ethers and amines. So an ether group has two carbon chains, which we'll denote just like we did on the last slide, looking at R and R prime, meaning that they may be the same, but they may also have different lengths, and they're attached by an oxygen. In contrast to that, we have an amine, which has a chain, and at the end of that chain is an NH2 group. When you look at amines, they're very similar to amides, with the amide being produced from the carboxylic acid and an amine, and they have the general formula that R and H bonds to C, double bond O, and then an R prime. That would be an amide. And that's a common group that you would see for people that are taking biology. That happens to summarize all the organic chemistry, organic derivatives that you need to be able to know and recognize, and leaves you in a position to be able to complete sections 9.8 and 9.9, the last two segments of organic chemistry and the last two sections for the year.